Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
Hello, I am Anya. Welcome to our show. Let's talk about physics.
Hello, I am Matteo. Welcome to our show. Let's talk about physics.
Let's talk today, in the first episode of this series, about the Newton's law and classical particles.
In our times, high school students dive into Newton's laws. They learn to calculate projectile trajectories using these laws. A bit of physics reveals the parabolic path of a projectile's center of mass. The projectile is real, but its center of mass is an abstract point for calculations. Newton's laws form the foundation of classical mechanics. A classical particle's movement is described by classical mechanics knowledge.
Anya, I agree with you.
For 3 centuries, soldiers have mastered the art of predicting where projectiles will land. Using the timeless laws of classical mechanics, they calculate trajectories with precision. Today, the same principles guide the paths of modern rockets. Newton's laws: solid, tested, and undeniably correct.
However, dear Matteo, we know today that if the masses of the classical particles are too large and gravitation is too strong, Newton's laws fail.
More than a century ago, Albert Einstein discovered the general theory of relativity. This groundbreaking theory redefined our understanding of gravity and the universe. While Newton's laws are still useful, they are only approximately correct. Einstein's theory provides a more accurate description of how gravity works. It explains phenomena that Newton's laws couldn't, like the bending of light around massive objects.
Anya, you know a lot. Let's summarize our discussion today.
Newton's laws are the backbone of classical mechanics. A projectile is a real classical particle, but its center of mass is an abstract point with mass for calculations. Newton's laws are solid, tested, and correct for calculating trajectories of projectiles, rockets, and macroscopic objects. However, for maximum precision in cosmological movements, we turn to Einstein's general theory of relativity.
Well, Matteo, still you are not completely correct. In these extreme cases, we should use a quantum general theory of relativity.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
Let's talk today, in the second episode of this series, about quantum mechanics and quantum particles.
Quantum mechanics is a fascinating subject tackled by university students in physics, chemistry, and engineering. It's a century-old discipline developed to explain atomic stability and phenomena like radioactivity. While its mathematical framework is universally agreed upon, theoretical interpretations vary. Quantum particles behave differently from classical ones, following unique laws of quantum mechanics. This field challenges our understanding of reality, offering a glimpse into the submicroscopic world.
Anya, I agree with you.
In the world of particles, not all particles are created equal. Quantum particles dance to their own waves, unlike their classical cousins. The nature of these quantum waves? Still up for debate. But the math behind them? That's a universal agreement. We solve wave equations to unlock the secrets of quantum waves.
You are correct, dear Matteo. The wave equations that should be solved are very well known. However, they are different depending on several factors.
When quantum mechanics emerged a century ago, physicists were already familiar with Einstein's special theory of relativity. This led to the development of 2 sets of wave equations. In non-relativistic quantum mechanics, the Schrödinger and Pauli equations were crafted. Meanwhile, relativistic quantum mechanics saw the discovery of the Klein-Gordon and Dirac equations. Recently, the Grave-de-Peralta's equations have been unveiled. These equations are both Schrödinger-like and relativistic. They offer a unified mathematical approach to both non-relativistic and relativistic wave equations.
Anya, you know a lot. Let's summarize our discussion today.
Quantum mechanics was developed to explain the stability of atoms and other submicroscopic phenomena like radioactivity. It's a well-developed physics discipline with universal agreement on its mathematical framework. The Grave-de-Peralta's equations unify non-relativistic and relativistic wave equations. Quantum particles are fundamentally different from classical particles. They follow the unique laws of quantum mechanics, unlike classical mechanics. Quantum particles have associated waves, unlike classical particles. This wave-particle duality is a cornerstone of quantum mechanics.
Well, Matteo, I think that we should add a commentary about the different opinions about the nature of the waves associated with quantum particles.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
Let's talk today, in the third episode of this series, about the wave-particle duality of quantum particles.
Particles, by definition, are spatially localized. A rocket, a car, and the Earth are classical spatially localized particles. Waves are extended, the opposite of particles. Yet, quantum particles are both waves and particles. A localized quantum particle exists where its waves do. Electrons can be found wherever their waves are, around the nucleus. To detect a quantum particle, find where its waves exist.
Anya, I agree with you.
In the world of particles, not all particles are created equal. Quantum particles dance to their own waves, unlike their classical cousins. The nature of these quantum waves? Still up for debate. But the math behind them? That's a universal agreement. We solve wave equations to unlock the secrets of quantum waves.
You are correct, dear Matteo. The wave equations that should be solved are very well known. However, they are different depending on several factors.
Recently, the Grave-de-Peralta's equations were discovered. These equations unify non-relativistic and relativistic wave equations. It's crucial to note, the math expressions aren't the quantum waves. We know quantum waves exist due to observed diffraction and interference. Only waves can create interference and diffraction phenomena. Experiments with quantum particles have shown these wave-like behaviors.
Anya, you know a lot. Let's summarize our discussion today.
Quantum particles are a mystery, being both waves and particles at once. Imagine a particle existing wherever its wave extends. To understand them, we solve wave equations for their mathematical expressions. But remember, these mathematical expressions aren't the waves themselves. We know quantum waves are real because we've seen them diffract and interfere in experiments with quantum particles.
Well, Matteo, we should clarify that real means here quantum waves exist. We are not talking here about the nature of quantum waves. In addition, I think that we should add a commentary about the existence of spatially localized quantum waves.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
Let's talk today, in the fourth episode of this series, about spatially localized quantum waves.
Like every particle, classical particles are spatially localized. Waves are extended. Waves are the opposite of particles. Nevertheless, Quantum particles are simultaneously waves and particles. A quantum particle can be found wherever its associated waves exist. But quantum particles are particles. Therefore, the waves associated with quantum particles should be spatially localized. For instance, in atoms, the electrons are confined around the nucleus. Atoms and molecules are small. Therefore, the quantum waves associated with free atoms and molecules are spatially localized.
Anya, I agree with you.
In atoms, the electric attraction between negatively charged electrons and the positive nucleus confines the electronic cloud around the nucleus. This means the electric field can spatially localize the waves associated with electrically charged quantum particles.
You are correct, dear Matteo. In heavy hydrogen-like atoms, the electrical attraction is so strong that the quantum waves associated with the electron becomes a point.
Did you know atoms with atomic numbers over 137 can't exist? Grave-de-Peralta's equations show their electronic clouds collapse. The 2021 paper, Making Relativistic Quantum Mechanics Simple, in the European Journal of Physics, explains it all. In 2025, a post on X, formerly Twitter, confirmed this finding. Even Grok, X's AI, validated the results. That's why the periodic table stops at around 100 elements.
Anya, you know a lot. Let's summarize our discussion today.
Quantum particles are mind-bending, right? They're both waves and particles at the same time. Imagine a quantum particle popping up wherever its waves are dancing around. In atoms, electrons are drawn to the nucleus like a moth to a flame, thanks to electric attraction. This electric field keeps the electron cloud snug around the nucleus, localizing those quantum waves. That's why we have 100 elements in the periodic table, not 1,000.
Matteo, I think that we should explain how this important result was obtained.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
Let's talk today, in the 5th episode of this series, about quantum waves collapse due to strong attractive electric fields.
Did you know atoms with atomic numbers over 137 can't exist? Grave-de-Peralta's equations show their electronic clouds collapse. The 2021 paper, Making Relativistic Quantum Mechanics Simple, in the European Journal of Physics, explains it all. In 2025, a post on X, formerly Twitter, confirmed this finding. Even Grok, X's AI, validated the results. That's why the periodic table stops at around 100 elements.
Anya, I agree with you.
Imagine a quantum particle trapped in a box, the simplest model for spatial localization. Using a Grave-de-Peralta's equation, we find the positive relativistic kinetic energy of this particle. This energy serves as a rough estimate for the kinetic energy of an electron in hydrogen-like atoms. The electron's potential energy is derived from a negative Coulombic electrical potential. Total energy? It's the sum of kinetic and potential energies. The electronic cloud size is estimated at the point of minimum energy. This model offers a glimpse into the quantum world, where energy and space dance in harmony.
You are correct, dear Matteo. In this way was correctly estimated the size of the hydrogen atom.
Did you know atoms with atomic numbers over 137 can't exist? Their electronic clouds collapse, thanks to Einstein's special theory of relativity. If we used the non-relativistic Schrödinger equation, they'd be stable. But reality confirms relativity. No atoms beyond 137. Relativistic kinetic energy is less than non-relativistic. So, electrons and heavy atoms lack the kinetic energy to balance potential energy. It's a fascinating proof of Einstein's genius.
Anya, you know a lot. Let's summarize our discussion today.
Ever wondered why there are only 100 elements in the periodic table? It's all about attractive electric fields and quantum particles. These fields can localize waves of particles with opposite charges. The internal energy of atoms? It hinges on the electronic cloud size. Attractive potential energy is negative, but kinetic energy is positive. In heavy hydrogen-like atoms, kinetic energy can't offset potential energy. That's the reason we have 100 elements, not 1,000.
Matteo, I think that we should talk a little bit about Einstein's relativity theory.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
I was planning to talk today, in the 6th episode of this series, about quantum mechanics and Einstein's special theory of relativity. However, Matteo insists on talking about gravitational atoms. Therefore, we will postpone our episode about quantum mechanics and Einstein's special theory of relativity. Let's talk today about gravitational atoms. Matteo, please, could you introduce the topic?
Thanks, Anya. A gravitational atom is a hypothetical atom formed by two tiny, identical, and electrically neutral quantum particles with mass. One particle is fixed in a point. Like the electron in hydrogen-like atoms, the other particle moves around the fixed one. However, the attraction between the particles is not electrical but gravitational.
The math behind gravity and electricity? Just a constant sets them apart. Imagine estimating the quantum wave size in a gravitational atom, like we did for hydrogen-like atoms. As with hydrogen-like atoms, the wave should shrink to a point at a certain mass. This point marks the largest mass possible for a gravitational atom. It's a fascinating blend of classical and quantum physics.
Matteo, I agree with you. Assume the quantum wave associated with the mobile particle collapses, the gravitational atom would become unstable. Let's see the details of the calculations.
Imagine a quantum particle trapped in a box, the simplest model for spatial localization. Using a Grave de Peralta's equation, we find the positive relativistic kinetic energy. This energy is a rough estimate of the internal kinetic energy in gravitational atoms. For potential energy, we consider the negative gravitational potential. The total energy of the quantum particle with mass is the sum of kinetic and potential energies. The quantum wave size is estimated at the minimum energy level. This model offers a glimpse into the complex world of quantum mechanics.
Anya, I agree with you.
In 2021, a groundbreaking paper in the European Journal of Physics revealed a fascinating truth. Gravitational atoms with mass larger than the Planck mass can't exist due to quantum wave collapse. This wouldn't occur if the non-relativistic Schrödinger equation was applied. Relativistic kinetic energy is too low to balance potential energy in heavy gravitational atoms. In 2025, a paper on social media X, formerly Twitter, confirmed these findings. Grok, the AI of X, also validated this result, highlighting a quantum classical frontier at the Planck mass. The collapse leaves the quantum particle nude, transforming it into a classical particle. This discovery reshapes our understanding of quantum mechanics and classical physics.
Matteo, this is a sensational result and interpretation. This makes a theoretical prediction that agrees with a huge volume of observational and experimental data.
The Planck mass is nearly 22 micrograms, a tiny measure in the grand scheme of things. This means elemental particles, atoms, and molecules are quantum particles. Their mass is much smaller than the Planck mass. On the flip side, everyday objects like tennis balls, cars, and rockets are classical, their masses far exceeding the Planck mass. The same principle applies to cosmological objects and the universe, making them classical too. So, while the quantum world is tiny and mysterious, the classical world is vast and familiar.
Anya, you are very intelligent. Let's summarize our discussion today.
Like attractive electric fields, attractive gravitational fields can also spatially localize quantum waves. The total internal energy of gravitational atoms depends on the size of the associated quantum wave. Attractive potential energy is negative, but kinetic energy is positive. There is not enough kinetic energy in heavy gravitational atoms to compensate for the potential energy. This explains why the world of atoms and molecules is quantum, but we are surrounded by macroscopic classical objects. The fact that atoms and molecules are quantum, but macroscopic and cosmological objects are classical, supports the validity of Einstein's special theory of relativity.
Matteo, I think that we should talk about gravitational interactions of a quantum particle with itself.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
In the 7th episode of this series, let's talk about classical gravity in quantum mechanics.
Gravity is the glue of the cosmos. It binds our solar system, galaxies, the entire universe. The solar system, a grand classical structure, is a masterpiece held together by gravity. But could gravity work its magic at submicroscopic levels? Imagine gravitational atoms. Could they exist?
Anya, any particle with mass can be considered formed by two halves that interact gravitationally with each other. This is the theoretical gravitational atom discussed in the previous episode.
So, if a particle's mass is less than the Planck mass, it dances in the quantum realm. Yeah, it exhibits quantum properties, like a tiny magician. But if its mass is bigger than the Planck mass, it becomes classical. This happens because the quantum wave associated with it collapses.
Matteo, do you know why macroscopic classical objects are formed by submicroscopic quantum particles?
Our entire body is a classical object because our mass is much larger than the Planck mass, which is only 22 micrograms. Yet, we're made up of quantum molecules and atoms, a fascinating paradox. It's like being a giant in a world of tiny wonders. So, next time you look in the mirror, remember, you're a masterpiece of physics.
Anya, this is a good question. Let's think about this.
In quantum mechanics, the center of mass coordinates simplifies the math of waves equations. The quantum waves split into two, one for the center of mass, one for the components. The center of mass wave shows the whole particle's movement. When the particle's mass exceeds the Planck mass, this wave collapses. The center of mass becomes classical, like rockets. But if components are under the Planck mass, they stay quantum. This duality explains why rockets are classical, but their atoms are quantum.
Matteo, this is a clever explanation. I like it.
Imagine a neutron star, a cosmic marvel formed by countless neutrons. Each neutron is a quantum particle, tiny and mysterious. Yet, the star's mass is immense, a giant in the universe. The movement of its center of mass follows the grand laws of classical mechanics, or Einstein's relativity. Astonishingly, these massive stars owe their existence to quantum particles. It's a dance of the minuscule and the massive, a cosmic symphony. A neutron star is a testament to the universe's wondrous complexity.
Anya, you are very intelligent. Let's summarize our discussion today.
The Planck mass is nearly 22 micrograms, a tiny measure in the grand scheme of things. This is why elemental particles, atoms, and molecules are quantum particles. Their masses are much smaller. On the other hand, everyday objects like tennis balls, cars, and rockets are classical. The same goes for cosmological objects and the universe. They're classical too. Macroscopic objects are fascinatingly made of tiny quantum particles. It's a dance between the quantum and classical worlds all around us.
Matteo, I think that we should talk about some far-reaching consequences of these ideas.
Wait, Anya. No so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
In the 8th episode of this series, let's talk about some far-reaching consequences of the existence of a classical quantum frontier at the Planck mass.
Most of the fascinating properties of quantum particles are related to the quantum wave associated with them. This is why classical particles do not have these properties. Quantum particles can be simultaneously in several states, can be entangled, and teleported. Imagine a world where particles exist in multiple places at once. Entanglement means particles are connected no matter the distance. Teleportation isn't just sci-fi, it's a quantum reality.
Anya, I agree with you.
Ever heard of Schrödinger's cat? It's both dead and alive at the same time. Sounds fun, right? But cats are too big for quantum tricks. Parallel universes? Super fun to imagine. But our universe is massive and unique. Quantum particles can teleport, but we can't. Our bodies are just too classical for that.
But Matteo, we already have quantum computers, which are using the fact that qubits could be simultaneously in an infinitude of different quantum states.
Classical computers rely on bits, which can only be in one of two states, 0 or 1. But here's the twist. Qubits in quantum computers can exist in multiple states at once. Step 1. Understand that qubits are quantum structures. Unlike classical bits, they can be in a superposition, holding multiple possibilities simultaneously. Step 2. Qubits can be entangled, meaning the state of one can depend on another, no matter the distance. This is where quantum teleportation comes into play, transferring states without moving particles. Final step. Embrace the future of quantum computing and quantum internet. Boom! Mind-blowing potential. No classical computer can match. Y'all see this? The quantum revolution is here.
Anya, you know a lot. However, did you know about the discussion about this topic recently published in X between Grok, the AI of X, and Professor Grave de Peralta?
The total mass of quantum structures in today's qubits is much smaller than the Planck mass. This means qubits can exist in multiple states simultaneously, perfect for quantum computing. But as technology advances and the number of qubits increases, their total mass could exceed 22 micrograms. At that point, the set of qubits become a classical object, limited to classical computations. This marks a hard limit for quantum computing, highlighting the classical quantum frontier. It's a fascinating boundary at the Planck mass, ripe for experimental exploration.
Anya, you must think about it. Let's summarize our discussion today.
Most of the fascinating properties of quantum particles are related to the quantum wave associated with them. This is why classical particles do not have these properties. Quantum particles can be simultaneously in several states, can be entangled and teleported. However, we cannot do these things with macroscopic objects. Quantum computing could be used for performing experiments demonstrating the existence of a classical quantum frontier at the Planck mass.
Matteo, I think that we should talk about the similitudes and differences between quantum mechanics and spirituality.
Anya, no so fast. We will talk about this stuff in future episodes of this series. This is enough for today. Ciao, Anya. I love you and we love our audience. See you in the next episode.
Let's talk about physics. Yes, from cosmology and the universe to the quantum world of atoms and molecules. From Newton to Einstein with a lot of curiosity.
In the 9th episode of this series, let's talk about similitudes and differences between spirituality and quantum mechanics.
Quantum mechanics isn't about spirituality, but it does share some intriguing vocabulary. Think about it. Ethereal souls and light energy quanta both lack mass. Like ghosts, neutrinos pass through matter unnoticed. There's a soul-body duality, much like particle-wave duality. Souls, like quantum particles, can be in multiple places at once, and spirits can be entangled. In today's world, Wi-Fi and electromagnetic fields are as omnipresent as the divine.
Anya, I agree with you.
Let's dive into the quantum world. Double-slit experiments show electrons can be in two places at once. This happens because their mass is smaller than the Planck mass. Humans, with their larger mass, can't be in two parallel universes. The universe is classic and unique, just like us. Photons and souls share traits, but souls aren't made of light. Spirituality and science both require belief. Spirituality asks us to believe in souls. Science asks us to believe in our ability to understand nature. Both realms challenge us to explore the unknown.
Matteo, it looks like we humans apply the same set of ideas for understanding different kinds of problems. However, physics is precise because math is the language of physics.
Quantum mechanics is fascinating, and you don't need math to get the basic ideas. But mastering it, that's a whole different ballgame. Advanced math is crucial, especially in modern field theories. Math helps physicists build precise and general theories.
Anya, this is good and bad at the same time.
Relying too much on mathematics could obscure the connection of the physical theory with the real world that the theory should help us to understand. In addition, this could transform theoretical physicists into an elite divorced from reality. Too much mathematical speculation in quantum mechanics has resulted in theories lacking observational and experimental support. The extremes often touch each other. Parallel quantum universes have never been observed. However, their speculative existence has fueled pseudo-spiritual theories.
Matteo, please, let's talk about physics.
Let's settle this. Engineering saves the day, every day. Planes fly, cars run, buildings stand tall, and Wi-Fi keeps us connected. Nuclear power and precise rockets, all thanks to engineering. Spirituality guides scientists, helping them overcome their challenges and guiding their souls needed of divine compassion.
Anya, you are very smart, and you also are a very ethical person. Let's summarize our discussion today.
Quantum mechanics isn't about spirituality. It's about observable facts. Yet, the language of both can sound surprisingly similar. Thankfully, engineering grounds physics in reality. And spirituality? It helps physics rise above its darker uses. In the end, both worlds contribute to a greater understanding.
Matteo, I think that we are ready to talk about quantum mechanics and Einstein's relativity theory.
Yes, Anya. We will start to talk about this in the next episode. Ciao, Anya. I love you, and we love our audience. See you in the next episode.